Okay, picking up where we left off on the last video, you will recall we focused on this document and we wrote our dyad loop equation that said WA plus ZA plus delta minus rotated ZA minus rotated WA equals 0. And from that, we jumped over to MathCad. We wrote that equation. We took the delta to the other side. We grouped the W and Z terms. We collected our W and Z terms, noting that that is a constant if we know the beta 2s, that's a constant if we know the alphas. Realize that for a 3-position problem, we can write this equation twice. This first version of the equation lets us travel from position 1 to 2. The second version of the equation lets us travel from position 1 to 3. And then these are two linear equations, two unknowns, using complex variables. The W's and Z's are the unknowns if we know the alphas and the betas, and we're going to pretend that we know all the alphas and the betas to make any progress on this. And if these are linear equations, they can be solved using linear techniques. So that's where we got to last time. So let's actually play with solving these equations by going back to the wing flap dyad synthesis. We've looked at this picture before, and we see P1, P2, and P3, and we see the alpha 2 and the alpha 3, and let's go ahead and enter those numbers. And let me see, I'm going to make the MathCad a little smaller so I can keep those numbers in front of me. And with that, let's see, I have my P1s, P2s, and P3s, there they are, and I'm going to have to zoom in on that to be able to copy those numbers. Let's go back to 100% and scroll. And so with this, P1 colon equal to 4.17 plus 5.821i times 1i, and P2 colon equal to 6.121 plus 5.719 times 1i, and P3 colon equal to 6.311 plus 4.795 times 1i. And then going back to the alphas, alpha, oops, I have to click back in here, alpha 2 colon equal to minus 20.4 times degrees, and alpha 3 colon equal to minus 45.5 degrees. Okay, with these, I can then, I'm going to make a copy of these equations, copy and paste. But I'm also going to say something like beta 2 colon equal to 15 degrees, and beta 3 is equal to 40 degrees, and I'll change that bold equal sign into a colon equal sign. And let's see, this says, I haven't got my deltas yet. Now that I have the p's, I can say that delta 2 colon equal to P2 minus P1, and delta 3 is P3, don't need caps, need caps lock, P3 minus P1, and I have just computed one W and one Z. And let's print that out. Copy and paste equals, and I'll have to move it down a little bit so it'll print. And those are my values of W and Z coming out of this computation. Isn't that impressive? And I'd say no, it's not, because we have to give this some meaning, and we really haven't given it any meaning yet. And the W's and Z's themselves aren't really what we're after. Let's go back and look at our picture. Here's the 4-bar. Moving an object in the way that we want to moving it, making it pass through P1, P2, P3, and having angle changes alpha 2 and alpha 3. But we don't have the 4-bar yet. How do we get the key points on the 4-bar? Let's go back to this picture and remember that ZA is a vector that tells us how to get from this pin joint to that interesting point on the machine. And W tells us how to get from the grounded pin joint to this pin joint. And we can use this picture to actually take our W's and Z's and learn the values of A and A0. Because all we have to do to find point A, which is a moving pin joint, that pin joint travels on a circle, is take our P1 and subtract the Z that we just found. Then to find our grounded pin joint, all we have to do is take our point A that we just computed by backing up through Z, and if we back up from there through W, we'll find our grounded pin joint. So going back to the MathCad, let's do that. And we will then say that point A, let me go ahead and use capital, is equal to P1 minus Z. And that tells us our moving pin joint for this 4-bar is right there. And then finally, A0 is equal to A that we just computed minus W. And there's the location of our grounded pin joint. So we have just computed one solution to the set of equations that says if we'll place a grounded pin joint at this location, and if we'll place a moving pin joint at that location, and if we know where P1 is, we can draw this picture, and that's one side of our mechanism. If we were then to change our guesses for the betas, then we could use that other solution and realize we're solving equations for the right-hand side rather than left-hand side. We could get a solution for the right-hand side, and together we would have an entire 4-bar. Let's I guess we can go ahead and do that, and what I will do is just copy these so I don't lose these. Copy, paste, and I'm going to copy these two and paste those two, Control R to clean up the screen. Okay, and now if I just change my betas, maybe I'm going to let this one equal to 30 degrees and 79 degrees. Then I get new W's and Z's, and I get new coordinates, but maybe I would choose to call this one a B, and this grounded pin joint a B0. And now having an A0 and an A, and a B0 and a B, that totally defines a 4-bar mechanism. I have no idea if it's any good, but I've gotten one pair of solutions to get to one 4-bar. I think you can see how tedious this would be now to just go back and forth between these guesses, generating solutions, and then somehow deciding whether these pairs of A's and B's are any good. And that's where we're going to need some graphics, first of all, to figure out if they're any good. But I want to go one step further with these equations and say we're not limited to just guessing the betas and getting one solution. We can actually get lots of solutions. So I'm going to first of all wipe out this right-hand side stuff, because anything we do on the left-hand side pertains to the right-hand side. And now I'm going to do this. I'm going to say beta 3 is, first of all I want a range variable, and let's make a little bit more room. So I'm going to say I colon equals 0 semicolon 360 degrees. No. Sorry. I goes from 0 to 360. Beta 3 colon equal to I over 360. Actually, no, I want to change this again. Let's say limit equal 360. Then I is going to go from 0 to limit. That'll let us play with that. and I over, start over, I over limit times 360 times degrees. Okay, now what I'm doing, why is that unhappy with the I? I may be just a little bit too high. Let's make that a bit lower. This value must be, I've got to put an I sub I right there, of course. Okay, and now I need to put i's in this equation. Sub I, and sub I. Now I need to get rid of some things like this, right? We'll just redo these. It'll be easier. If I were to, let's say, k colon equal to 7, and let's just print out item number 7 and 7. Then here's my W number 7, or my W number 15. If I put a K there and a K there, then I could see all of the different WZ pairs that I have, and then I could calculate different A values. So A sub I is P1 minus Z sub I, and I'm going to get lots of different A's, and I can then say that A0 sub I is equal to A sub I, minus W sub I. Same equations I had before, but now I'm doing a large number of calculations. Now, what's interesting is that each A and A0 pair is one machine, but I've got a sampling of an infinite number of machines here. Let's go plot these points and see what they look like. So let's go click here, bring up the plotting toolbar. Where is the plotting toolbar? Okay, we'll do a graph like this, and I'm going to plot the imaginary of A sub I. No, I'm going to plot the, yes, of A sub I. No, just A, that should be enough. Versus real of A. And what's interesting, and really not to be expected, is that all of these A points fall in a circle. Let's make this bigger and explore a little bit. And let's go change this. Instead of a connected set of lines, let's instead plot symbols. Let's plot X's, and we'll leave that to be red, and we'll turn off the line, and we'll apply that. Okay, and so all of these different A values, and each A value is a different solution to the set of equations that came from a different value of beta 3. Now what I didn't say is this is different values of beta 3 while holding beta 2 constant. That's why it's only one infinity of solutions, or one sampling of infinity of solutions. What do the A0 points look like? Let's go plot those. Comma, imaginary A0 versus the real, comma, A0. Get a different circle. Let's go plot those as points, not lines. And so the blue one, let's use circles. Let's use plus signs. And those will be blue plus signs, and we'll turn off the line, apply that, okay. Okay, and so what we see is the A0 points all lie on this circle. The A points all lie on this circle. Now, where is one solution out of this thing? Well, one solution would be a link connected to an A0 point to ground that then moves to the right corresponding point over here. What do I mean by corresponding point over here? Well, we would need to pick, say, a value of k, and I'm going to, well, I'll just redefine it. Let's say that k colon equal to, again, point number 15, and then one solution would go from a sub k to A0 of k. That would be one grounded pin joint, moving pin joint pair. That's one solution. Then if I change the value of k to 48, I get a different solution. We can indicate that on a graph like this by actually, say, drawing the a sub 0 a point. So let's add that. And what I'm going to do is I'm going to define some geometry called link. Link sub k colon equal to a 2D vector one row, 2 columns. Okay, and I'm going to put a sub k there and a 0 sub k there, and so this is an etch-a-sketch kind of drawing of just a straight line. And I think I have to transpose that, and now I can print over here the imaginary part of link sub k versus the real part of link sub k. And let's see what I get here. And let's k equal to 1. And I'm not seeing anything happening. Let's go take a look at how the traces are set up. This one is a dotted line. I want to make it a solid line, and I'm going to make it pretty heavy. And I'm going to make it black so that it's a bit easier to see. Okay, apply. Ah, there it is. It was in a spot that's very hard to see. Let's, okay, now let's play around with values of k and find something maybe easier to see. Let's try 300. Let's try 200. Okay, and this is a particular solution to the problem. Now you can see that I'm looking at a sampling of an infinite number of solutions, but still playing with this k thing is kind of tedious. So I'm going to show you a new MathCad tool, which I think you'll like, and I'm going to insert, let's see, it's a control and it's a slider. And I'm going to let this slider determine my variable k. And I do need to set some properties on this slider. Let's see, is it inputs? Nope, that's not the right way to do that. Let's see, where is it? I want to edit it. There we go. I want to let this go from 0 to 360 to cover the full range. And now if I want to see different solutions for k, rather than typing and replacing k all the time, let's get rid of that, then this slider will let me change the value of k. And I've got 360 different solutions on here. A connection between 2 points is representative of one solution, and from this I can see that my moving pin joint would have to be there, my grounded pin joint would have to be there, and I can look at all of these solutions. Now, what do I have? I have the solution to my dyad synthesis equations, which gives me half of a 4-bar, and half of a 4-bar is a grounded pin joint and a moving pin joint. Okay, but that's not a full machine, and I still have no way of telling if any of these are any good. Now, the other thing that's going on is this particular set of infinite solutions came from only one choice, a beta 2. If I change my beta 2 to some other number, like 79, I get a totally different set of solutions. And so to search through all of this kind of stuff, I'm probably going to need another slider. Play with beta 2, play with the value of k, and at some point see if I can find good solutions out of all of this mess. But there's no basis on this picture right now for being able to declare a solution good or bad. In the end, I've got to know what problem I'm solving, and I've got to know the definition of good or bad. Let's go back and look at the wing flap problem. And we had a definition of good or bad in the wing flap problem. What was the definition of good? That my A0 and B0 points, my fixed pin joints, had to be in this region, and that in position 1, my A and B points had to be within here. The only way I could tell that in the MathCad document that I'm working on is I would need to draw this region, and I would need to draw that region and see where my points are landing. And we're going to see a MathCad document in a moment that does all of that. It would be my standard dyad synthesis document where every time I have a new problem, I need to do a drawing of acceptable ranges for the pin joints, and I also need to do a drawing of the object that's going to be moving. And we'll see that in the next video.